Okay, welcome everyone to the foundation seminar once again. Things are a little different on the Zoom, and this time around we're using this webinar system. So to all the guests who are attending on Zoom, if you have a question, you can raise your hand or type something in the chat, and I will allow you to talk, and you can you can ask the question of the speaker directly. Of course, for the people in the audience, you can just raise your hand and I can, in case the speaker can't see you, then you can, I'll just call on you and you can ask a question. And I also want to make sure that from now on, I have a co-organizer for the foundation seminar, which is Delilah, who's right here. So please also communicate with her if you have any questions. Without further ado, our speaker today is Professor Sam Fletcher, who's a professor of philosophy of physics at the University of Oxford and who has worked on a wide range of topics. But today he's going to talk about the definition of space-time singularities. So Sam, floor is yours.
Thanks very much, Siddharth. And it's nice to see you all, even if it is very far away. I can't quite see the individual faces of the people in the room. So if you have a question and I don't recognize you or see who it is, I'll try to identify you by kind of like what kind of color shirt you're wearing. I hope you don't mind that. So the first part of the talk, I want to give a little bit of potted history about the development of ideas about what space-time singularities amount to or how they should be defined that arose from work done by folks like Bob Garroch and others in the 1960s and early 1970s. One of the interesting things that came about from this work is that it really made people have a deeper think about what exactly space-time singularities amount to in a theory like general relativity, where we don't have a background structure with respect to which we can identify gaps or undefined fields or so on. Then I'm going to go on to some issues of interpretation that one kind of definition that some people have settled on in the 1970s. So John Ehrman, for instance, the philosopher of physics, in his 1995, I believe it is, book, Bangs, Crunches, Whimpers, and Shrieks, describes this particular notion of space-time singularity. It's related to this notion of B-incompleteness that I'll describe in this section as a kind of new orthodoxy. I'm not sure I'm totally convinced that he was accurately describing what was considered orthodoxy in the 1990s, but in any case, it serves as a kind of definition that was supposed to solve some issues with prior definitions of space-time singularities. But they've always had this notion of B-incompleteness has always had interpretive issues. And so I'm going to present in the third section some very simple new results that I think help us understand what B-incompleteness amounts to, and at least in my view, show that it's probably itself not a very satisfactory notion of space-time singularities. Okay, so let's get started. Now, as I was alluding just before, the project here is to try to understand what space-time singularities are. But I think that if you're not already compelled by that, it might be worth spending a moment or two to describe why it matters. As you can imagine here, we have a space-time diagram describing black hole formation. Now, one of the things that many folks are interested in, as I'm sure at the BHI you know, is the extent to which, or the circumstances under which, the formation of singularities points to some sort of deficiency in current physics. But I think that it also offers a more precise question, answering this question about what singularities or space-time singularities are, but the question of what's really new in general relativity. I think that people who are interested, like me, in the history of intellectual ideas, especially ideas that we find in our best scientific theories about the nature of the world, are interested in new things we really learn, like really conceptually novel developments in theories. They're not just variations or harder to say are continuous with past developments. And there's some argument to the effect that space-time singularities are one kind of such feature in general relativity. But if you do want to argue for that, you need to be a bit, I think, precise about what singularities are supposed to be. Now, as I was alluding before, if you think that the presence of singularities indicates a deficiency in a theory that ought to be resolved in a successor theory, then your goal in that successor theory, like a theory of quantum gravity, is singularity resolution. To resolve singularities, of course, you have to know what exactly you're resolving. Uh, it's important to have strong identification conditions to be able to know whether or not a theory is satisfactory at resolving the singularities that are supposed to be. Now, the history of the ideas of thinking about space-time singularities begin in analogy with singularities that we find in previous field theories like electromagnetism. So here we have a field diagram and a potential. These are familiar to you. They're familiar to all of us, in fact, that if we try to describe a point charge in electromagnetism, we find a singularity in the field, a point at which we can't smoothly define a value for the field or the electromagnetic potential for that matter. And this is contrary to a kind of expectation that these fields are everywhere in space, well defined. And so we can identify singularities in a physical field by points of space or space-time where they're ill-defined. The problem, of course, is that we can't quite do that in general relativity, because if the field that is the thing that we want to be considering, whether it's singular or not, namely the space-time metric, is itself constitutive of what it means for points or a point event to be a part of space-time, there can't, by definition, be any points that don't have the metric well defined at them. Such points wouldn't be a part of the smooth Lorentzian manifold that forms the model of general relativity. So we need to find, or at least this is how the history went, some proxies for points at which the metric is well defined or missing points, because um, if there aren't any points by definition of a smooth Lorentzian manifold at which the metric isn't well defined, then there are points missing at which perhaps the space-time metric is indicatively singular. So one idea that people had was to try to find particular fields, the metric or curvature or some other concomitant of them that diverges as one follows a curve in a particular direction. Now, this way of thinking about things only really works if you have a particular coordinate representation of these tensorial quantities, because by themselves, they don't directly admit any preferred metric that allows you to talk about them diverging to infinity or so on, like a real quantity would. And so instead of the fields themselves being divergent, one idea would be looking at divergent components or scalar concomitants. The problem is that with these sorts of quantities is that there are examples that one construct. Garroch constructed some examples in the 1960s, and others found others where scalar components, these scalar components don't diverge, but there's some prior sense in which we want to believe that the space-time is singular. And so a kind of idea that people landed upon was, instead of using components of the field to try to identify the missing points, identify, as it were, the points at which the space-time metric would have been singular if it had included them, to identify curves themselves that you think in some sense end prematurely. The idea here is that if you have a smooth curve that you would otherwise have expected to be um, extendable, for instance, because it's a time-like curve and it only has a finite proper magnitude representing, say, a finite duration of some process, you might expect that it ought to be continuable, extendable, just as it would be if it were in Minkowski spacetime, especially if it were a geodesic. And so if we can identify curves that end prematurely, that is to say, future inextendable curves that have a finite magnitude, especially time-like ones, then we've identified a proxy for missing points, a way in which we can identify spacetimes as being singular. Now, this might even work if one disavows the whole idea that somehow these are proxies for the idea of a missing point or an ill-defined point. You might eventually, in this process, come to think that maybe this is a more fundamental idea and it's not really a proxy for the idea of a missing point. That's an advantage of this kind of conception. So what people settled upon was a notion, at least initially, a notion of geodesic incompleteness. So I have some technicalia of the definition up here. The main idea is we start with some space-time and some half geodesic. And we can classify these half geodesics into two types, the incomplete ones and the complete ones. The incomplete ones are simply the ones whose upper parameter is finite, and the complete ones are the ones whose upper parameter is infinite. Then we can classify the curves also into the inextendable and the extendable ones. I've already alluded to that as well. The extendable curves are exactly those that you'd imagine. These are the curves that can be extended. They match another curve that has a larger proper parameter, and the inextendable ones don't. That's all that this technicality is just describing here. So with this preliminaries, we can say that a space-time is geodesically incomplete, in particular reference to the type of curve that witnesses it, whether it's a time-like curve, a null curve, or a space-like curve, just in case it has at least one inextendable incomplete geodesic of that type. And it's an interesting feature that, logically speaking, these three types of geodesic incompleteness are independent of one another. So a space-time can have one without necessarily having the others, but it, of course, can have all three. So when a space-time is geodesically incomplete, there's some sense in which the space-time, you might say, has some points that are missing from it that ought to be included. Now, there's a question about whether or not such space-times ought to be regarded as singular or not. Generally, people have taken it to be a sufficient condition when the space-time itself is also inextendable. I tend to be a little bit more liberal because I think that if you have an extendable space-time, that it can also count as being singular, even if, as it were, the region that contains the singularity is a part that can be extended. I think that's just an unusual feature of incomplete spacetimes. Okay, so what's important about this sort of definition is that it's also the kind of definition that shows up in many of the singularity theorems. Many of the singularity theorems are concerned with um, indicators or conditions for geodesic incompleteness. And if you take geodesic incompleteness to be a sufficient condition for a spacetime being singular, then those theorems do what they say they're supposed to do. They provide sufficient conditions in which a spacetime is singular.
Is this what Hawking and Penrose had in mind?
Yes.
Excuse me, but I think you need, this is not quite enough now. I mean, you need that, I think you can construct such curves in Minkowski space, right? Where you have that as you approach tau, the tangent vector of gamma doesn't converge. So I think you have to consider broken curves, no? So piecewise smooth curves.
Didn't quite hear all of that. I'm sorry.
Okay. Maybe I want to consider piecewise smooth curves here, because you can think about, again, in your definition of gamma is incomplete, for instance, if you have a curve which, or you only look at geodesics here, not necessarily about general curves. Is that what you're saying? Sorry. Okay. But in principle, you could have that the tangent vector doesn't converge. But okay, if you look at geodesics, then that's correct. Yeah. Sorry. Yeah.
Yeah, good. I'm glad we're on the same page, but I think you're already picking up on one of the issues with this particular condition. It can't be a necessary condition for space-time to be singular. It might be sufficient, but it can't be necessary precisely because it only concerns geodesics. And
It-
you might think that it's possible for there to be curves that are we would expect to be extendable that are not, but that are not geodesics. And this particular definition doesn't cover those curves. Indeed, one of the things that's interesting about some of Geroch's work in the 1960s about this is he at least constructed some examples of space-times that were geodesically complete in all three senses, but had incomplete curves of bounded acceleration. I wonder whether this is the sort of case that you have in mind.
Yeah,
Sam, we have a quick question from someone online, so I'm just gonna let them talk. Parts, go ahead.
Hi, Shem. So, if this incompleteness of the geodesic is the part of the manifold,
Are you talking about the definition of geodesic incompleteness or the incompleteness of a curve? Sorry.
I'm talking about the definition of the singularity where you define this M is the manifold is differentiable on GAP. So you define three kind of curves here, geodesically incomplete. So
Yeah.
are these geodesic incompleteness is a part of manifold or something else?
Yeah, okay. I understand your question better now. So, geodesic incompleteness here is a property of a Lorentzian manifold. It's witnessed by a particular type of curve, but it's a property, it's a global property of a space-time. So it's not a property that accrues to particular points. One of the things that's particular about this definition, which is different from the kind of singularity definition that we often see for physical fields like electromagnetic fields, is that those former sorts of definitions identify points of space or space-time where the field is singular. And here there's no points of space-time that are being identified as the singular points. Rather, it's the space-time as a whole which is identified as being singular, and that's the sense in which it's a global property. Does that go some way to answer your question?
Yes, I see. Thanks.
Cool. Other questions at this point?
I think we're good for now.
Okay, cool. So let's go on to some of the problems of interpretation. So as I was just alluding, one of the nice things about geodesic incompleteness is that it is really amenable to being treated in lots of different contexts that make it connect with the kind of technical tools that folks like Geroch and Hawking and Penrose use to prove their singularity theorems. But as we've just been discussing, it doesn't seem like it's necessary for being singular because if you really think that, for instance, identifying missing points is the thing that needs to be done in order to really give a full definition of space-time singularity, it doesn't do that. Or if you wanted to localize the singularity insofar as that's desired. And as I was just describing in the discussion that we had, there's geodesically complete spacetimes that contain inextendable curves of finite length and bounded acceleration. And you might think that those sorts of curves exhibit the same sort of behavior. That is to say, they have curves that they contain curves that we would expect to be extendable that aren't. And if that underlying conceptual idea is really the adequate proxy that we're using for space-time singularities, then this particular definition doesn't capture that. So in order to go on to the kind of successor definition to this, which is based on this concept called B-incompleteness, we'll have to introduce some technicalia. Now, one of the reasons why I want to phrase things in this sort of way, maybe I should back up and I should say two things. If you're super familiar with this literature, you'll know that there's different definitions of B-incompleteness. There's a geometric definition that I'm suppressing for now because the analytic definition that I'm going to be giving is more amenable to the kind of line of argument that I want to give, but the definitions are equivalent with one another. The other thing that I wanted to mention is that going through the technicality here is intended to give you the impression that it's not really clear what the physical significance of many of these things is supposed to be. And so that's intentional because I'm going to come back to the point that it's kind of unclear how to interpret this particular notion, even if it has a certain mathematical elegance to it. Okay, so now let's briefly go through some of these details. For this new notion, what we want to do is we want to be able to capture curves that we think ought to be extendable that aren't, but do so in a way that it is inclusive of geodesic completeness, but includes more curves. Now, one of the big problems is considering what to do regarding space-like, null, and time-like curves. And so the definition of being incompleteness is designed to try to be inclusive around these ideas. What it does is it considers like geodesic incompleteness as a class of witnesses, smooth half curves. But in this particular case, we're going to associate with the half curve and an orthonormal frame. You can pick a particular point on the curve to associate it and then just parallel transport it along the curve. That's what we're going to do, and we'll let E of S be the frame parallel transported to the point of the curve that has the affine parameter S. And we'll call the V the components of the tangent vector for that curve with respect to that frame. So we've got a collection of 4 different components, and this allows us to define a quantity called the generalized affine length of gamma with respect to this frame. You'll notice here that we're just taking the Euclidean magnitude of the components of the tangent vector, and we're integrating them along the curve. So that's giving the generalized affine length. And the integrand here is called the generalized affine parameter. As I mentioned, part of the reason to do this is to try to be a way which is inclusive of space-like curves, time-like curves, and null curves. And the treatment of null curves here is in particular part of the reason for some of the complications. So one of the nice results about this is that whether or not the generalized affine length of a curve is finite or infinite is independent of which orthonormal frame you pick. So if it's finite for some frame, then it's finite for all frames and vice versa. So this shows that the particular frame that you pick is a kind of calculational device. It doesn't necessarily represent something important, but what is important is the finiteness or infiniteness of the generalized affine length rather than the particular magnitude that it gets. Okay, so this is a way of describing, in a way, curves which are finite or infinite in a kind of generalized way. I have a bunch of slides on why the name here, generalized affine parameter, comes about, but I think it's mostly of mathematical interest rather than physical interest. I'm happy to come back to these, but I think I'll skip over them for now in the interest of time. Okay, so now that we have this generalized affine parameter, we can now give a definition of B incompleteness. We can say that any particular curve, B incomplete, just in case its generalized affine length is finite for any with respect to any frame. And of course, based on the lemma that we discussed before, it's finite for any frame just in case it's finite for one frame.
We have a question in the room.
Yeah.
Yeah.
Sorry, I think I missed something. In your previous definition, you said it's Euclidean norm of some sort. You're forgetting the fact that you're working with a pseudo-Riemannian space-time. You're just ignoring the signature altogether. Is that how it works?
That is a bit of how it works. Let me go back here. You're right to identify here that I'm using a kind of Euclidean norm rather than one of Lorentzian signature. And part of the reason for this has to do with the fact that if you want to apply this sort of definition to null curves, you always get the answer um, if you use the Lorentzian signature that the parameter is always going to be zero. And it just has to do with the fact that the length of null curves is always going to be zero. And so you can't easily make a distinction between the curves that end prematurely and the ones that don't via the magnitude of the curve. So the whole idea around this particular way of doing things comes about as a way to try to identify or make a distinction between curves that we expect to be continuable and ones that aren't, using a different kind of mathematical apparatus. But you're right to identify the difference with the Lorentzian signature in this integrand here. Does that go some way to answer your question?
Oh, yeah, sure. I'm just surprised that something this violent can still be useful.
Yeah, I agree with you. And the integrand itself, of course, is relative to some particular choice of frame. It'll give you totally different numbers if you pick a different frame. So the usefulness of this indeed really depends on this lemma here. It's really this distinction between the finite and the infinite ones that we really care about. Okay, so coming back here. So then the definition of a spacetime being B complete is then given as a space-time that has a continuously inextendable B-incomplete smooth curve. So it's analogous to the notion of geodesic incompleteness. It uses this notion of incompleteness instead. Now, you'll also notice here that there's a difference here that it also uses this notion of continuous inextendability. So, so just as the previous question revealed, this particular quantity here, the generalized affine parameter that gets integrated, it does some violence to the structure of relativity theory. It's not really clear what it has to do, what its physical significance is. And I'm not the first person to pick up on this. So here's a nice quote from Eric Curiel, with whom you may know Eric. He writes that the chief problem facing this definition of singularities is that indeed the physical significance of generalized affine length is opaque. And it's unclear what the relevance of singularities defined in this way might be. I agree with him about this, and I think that there's two features here actually that we can identify. One is the definition of B incomplete smooth curves, and that has to do with the generalized affine length that we were just discussing. And the other aspect has to do with why continuous inextendability rather than smooth inextendability. I'm going to come to each of these in turn. And to come to them, I want to give you some new simple results that I think help shed light on how to interpret them.
We have a question from Zoom, just a minute.
Sure, go ahead.
Go.
How do we classify this time-like and null or space-like incomplete smooth curves? Because there are certain kinds of singularities which we call the null singularity or time singularity. And then in the Schwarzschild black hole, we have a space-like singularity.
Yeah, it's going to be this in the same way as with the geodesic-based definition. So this particular curve gamma, right, we can say that it is space-like, say, be incomplete, just in case it's a space-like curve that has a finite generalized affine length. And similarly for null curves and for time-like curves. Does it answer the question?
Okay.
Okay,
Thanks.
cool.
Other questions while we have? Okay. Go ahead, Sam.
Okay, right. No further questions then. So let's go to some new ways of trying to understand what this definition really is doing. Okay, um, so here's the first result that I think sheds a little bit of light on what's going on in this definition. And this is focusing on the be incomplete part of the definition. Okay, so now let's consider any continuously inextendable, smooth, time-like half curve. It's going to be a curve that standardly in relativity theory, we can say represents a massive test particle. And let big E be its energy relative to a particular frame. So remember, this is just directly related to the magnitude of the time-like component of the tangent vector in that frame. The more that it's aligned with the frame, the more that the energy is just going to be given by mc squared, and then the more that it's not aligned, it'll pick up a component relative to the momentum of the particle in that frame. So one can show then that this particular curve gamma is B incomplete if and only if the integral of this energy is finite for some frame. So to give you an idea about what's going on here, let me just quickly draw a couple of examples. So the situation that I have in mind is a situation where this is the kind of curve that you're integrating, which is going to be the energy with respect to some particular frame. And similarly here. Apologies for my shaky handwriting. I haven't done this since the COVID times, so I'm not quite as practiced as I used to be. So if this particular function, say, grows towards tau, something on the order of, for instance, tau minus s, then when you integrate this, you'll get something which is on the order of a function which is log of tau minus s. And so that curve and that one will blow up as you integrate it. But on the other hand, if it's on the order of something like this, the integral will be finite. So depending on the growth rate of the energy, this particular integral will be finite or infinite. Now, effectively, therefore, the result shows that B incompleteness puts a certain bound on the growth rate of the energy of this putatively incomplete curve. And it identifies the curve as having the property of B incompleteness just in case this growth of the energy is too large. Now, and this particular condition here gives a precise definition to what too large means. Now, what I hope that your reaction is why that? Why is that important? Why does that growth rate matter at all? And I think that you'd be right. The reason why I think you'd be right is that now that we understand what this condition is doing, we can see that it has a certain kind of arbitrariness to it. There's some corollaries of this that we can discuss that I think are interesting. But what's important here is that B incompleteness, by putting a bound on how quickly energy can grow for a test particle whose world line would be the witness to B incompleteness, we can ask why this quickly. And I think that this gives a deeper voice to the kind of complaint that we saw Eric Curiel giving, that this definition has a certain kind of arbitrariness to it. And now we've identified one aspect of this arbitrariness. The way that B incompleteness captures or allows for accelerating curves to be witnesses to incompleteness is that it requires that they have a certain bound on their energy increase if they're time-like curves. But the particular bound that's given doesn't really have any independent physical justification. So now let's go to the extendability part. You'll remember that the definition of being completeness involves continuous inextendability rather than smooth. To illustrate why that condition is the way that it is, let's consider a different sort of example. So this example is Minkowski spacetime. And here we have a smooth curve whose forward velocity has, in a standard chart, adapted to the symmetries of the spacetime. So it's a Lorentzian chart, these particular components. And it looks something like this, yeah? So it's wiggling back and forth. It's undergoing sharper and sharper accelerations, but the magnitude of its oscillations are also decreasing. So you can show that this curve is of finite length, and moreover, its energy is constant because even though it's undergoing more violent accelerations, the amplitude of the accelerations is decreasing. Moreover, you can show that it's smoothly inextendable. It can't be extended to P because all of the higher order components of the curve, namely its tangent vector and its acceleration and so on, don't converge to any particular vector. So it's not smoothly inextendable. But why isn't therefore Minkowski spacetime be incomplete? Why doesn't this curve provide a witness for Minkowski spacetime to be incomplete? It's because B incompleteness only requires continuous extendability. And so gamma is continuously extendable to P, even though it's not smoothly extendable. So part of the way that B incompleteness becomes helpful and fruitful is by weakening the extendability conditions when you're applying it to situations in general relativity, so that Minkowski spacetime isn't accidentally classified as being in a singular spacetime. But the problem with this is that this concept of continuous extendability is a purely topological concept. You don't need it to have any metrical structure in order to identify curves that are continuously extendable or inextendable. And so this notion of extendability is more topological in character than causal. This particular notion, this concept that goes into the notion of B incompleteness, in other words, explicitly abstracts away important characteristics of the structure of space-time that we think have physical significance. And so for that reason, it's also capturing something which is misaligned with what we're representing in general relativity. So we can capture this sort of idea and some others related to it using the following proposition. So let's consider any smooth half curve with components with respect to some parallel transported orthonormal frame, and another smooth half curve, but specifically is in Minkowski spacetime. And the two half curves are matched in the sense that they have the same components with respect to some orthonormal frame. Then the first curve is B incomplete if and only if the corresponding curve in Minkowski spacetime is continuously extendable. So what that means is that the way that B incompleteness captures a notion of spacetime singularity is that it identifies a kind of notion of a counterfactual missing point. These are the points that would have been included had the spacetime been Minkowskian, in the sense that it would be the spacetime that includes the same curve understood as a curve with the same components. Now, what's interesting is that the above is still true if Minkowski spacetime is replaced with any B-complete spacetime. So this is independent of the particular geometrical structure of Minkowski spacetime. But what's important about this is that this notion here shows that the missing point notion being captured by completeness is a topological notion, which is just very simply expressed within Minkowski spacetime, rather than a geometrical one, which should include just continuous extendability, but smooth extendability, because we think that the the first order, second order, and so on structure of curves has physical significance. It represents the velocity and the acceleration and so on. Okay, so I think that how B-incompleteness fares overall depends a little bit on which conception of space-time singularities you adhere to. If you are really keen on this missing point idea, I think that it does capture a counterfactual sense of missing points through continuous extensions of curves in Minkowski spacetime. But if you adhere more to the incomplete curves idea and think that this is better at capturing the essential idea of spacetime singularities, I think that the definition is less well motivated. Why the particular bound on the growth of energy? And why continuous extensions rather than smooth extensions? Indeed, I think that even if you're an advocate for this missing point conception of spacetime singularities, you'll have to chafe a little bit at the fact that the notion of missing points here are points which are missing purely in a topological sense, rather than a geometrical one. So I want to suggest very briefly that an alternative that's closer to the incomplete curves conception would allow us to consider smoothly inextendable curves of bounded acceleration. I think this captures some of the original intuitions about why we had to go beyond geodesic incompleteness in the first place. I think one of the reasons why perhaps this particular notion or particular definition of space-time singularities hasn't received as much attention is that when this notion of B-incompleteness was first formulated in the early 1970s by Schmidt, Schmidt gave it a very nice, very mathematically elegant, geometrical, I would say even topological. It involved a certain kind of bundle structure and completions of bundle structures, in particular the frame bundle. That elegance, I think, gave it some weight. This particular notion here, as far as I'm aware, doesn't have such an elegant construction, but I think that it might be more physically significant than the B-incompleteness definition. But because folks have mostly focused on geodesic completeness and on occasion B-incompleteness, there are fewer results regarding this other notion, this other definition. My conjecture is that many of the results that people can get with B-incompleteness can also be accomplished using this sort of definition in physically significant cases, but I haven't done the work to show that yet. I'm interested in what you think. That's the end of my presentation. Thanks very much for your attention, everyone.
Okay, questions also on Zoom, if please raise your hand and I can allow you to talk. Questions? Ramesh.
This goes back to early in your talk when
Yes.
you talked about divergences of quantities as a
Yes.
possible definition of singularity. And you were talking about these scalar quantities that may blow up. I have always looked at the Kretschmann scalar as a pretty sensible quantity. So in what way is it inadequate? Is it too liberal and brings in all sorts of good spacetimes and calls them singular, or is it the other way around, that it misses a few obvious cases? What's wrong with it?
Yeah, I think that it's going to be it's possible that it has both. Maybe I can try to describe in abstract terms some examples that might illustrate this. I have to say, though, before I give the examples, one of the things which is treacherous about this particular line of work is that sometimes it trades on people's just bare intuitions about whether a space-time ought to be regarded as singular or not, which makes it difficult sometimes to adjudicate. But maybe I give you the examples and see what you think about them. So one is an example where you take a patch of or not a patch of Minkowski spacetime. You take a spacetime like Minkowski spacetime, and you transform it by a conformal factor that provides a direction in space-time where curvature, in particular, say the Kretschmann scalar, is growing slowly without bound. In that space-time, you have a curve whose Kretschmann scalar is not bounded everywhere. And if my recollection is correct, that if you adjust that if you adjust this appropriately, you can have it so that uh, you can produce it with curves where the explosion or the rise to infinity of the Kretschmann scalar can be along either an incomplete curve or a complete curve. So if that's right, then you might think that if the unboundedness of the scalar is supposed to be sufficient for the spacetime to be singular, and you pick one of these versions where the curves are all complete, then it would be a case where you think that the spacetime ought not be regarded as singular, but is still regarded by this particular criterion. My recollection is that it's also possible, although the details I don't remember at the moment. I think it's in one of Giroch's papers, though. I think also it might be in the paper that I mentioned earlier on. Um, the What is a Space-Time Singularity paper from the 1960s, where you can construct examples where all of the scalar um, uh, concomitants of the curvature are all bounded, but it still has incomplete geodesics. And so in this particular case, the criteria would come apart in a different way. Now, it's always possible to react to these sorts of examples to say my intuition is stronger in a particular kind of case than another kind of case. And it makes us think, or at least it makes me think that we ought to have some sort of independent way of adjudicating this rather than just having a battle of intuitions. I don't know if you think the same way about it or not.
No, thank you. This is very helpful. I will go
Okay.
and look at all those articles.
Okay, good.
Yeah. So, but in your definition, open subsets of Minkowski, like bounded subsets of Minkowski space are singular. I mean, so, or like, sort of to me, that's not. I mean, they have those curves, right? Or is that what you're saying?
Yeah, so an open proper subset, you mean?
Yeah, just like taking an open bounded subset of Minkowski spaces.
Yeah, this is related to a comment I made earlier on that in some definitions of space-time singularities, people want to demand also that the space-time be inextendable because they're thinking about cases like the one that you're presenting. In the cases like the one that you're presenting, you want to say it's not really singular because where there's more of the space-time to be filled out that has been left out of the descriptions, say. And once those are filled in, you realize that the curve you thought was the witness to the space-time being singular is in fact extendable. So I think that oftentimes, and you'll have to tell me whether this is your opinion as well, folks who have this intuition have the intuition that incomplete, excuse me, extendable spacetimes are not physically significant. They're only abstractions from or portions that we're examining for technical convenience of a real physically significant spacetime. And so they would add the condition that for a spacetime to be singular, it also has to be inextendable. I think that it's that extendable spacetimes can represent real ways that that spacetime can be. And so for that reason, I don't impose that condition in the definition that I give. But if you wanted to impose that condition, I think that that it wouldn't change any of the other details in the story that I gave.
I'm just saying that like, I mean, open subset is completely flat. Everything is beautiful about it. So to me, it seems awkward to call this a singular spacetime. And I think that what you said that talking about inextendability in whatever category you're interested in, I mean,
seems like the more natural notion of the single space time. Yeah.
Yeah, I do see that point of view. I think a lot of folks think that the default in the space time, right? Maybe default is not the right word. That singularities are caused by or are the result of some sort of um, um, substantially large field, some sort of not nice properties. You use the phrase, portion of a flat spacetime, like Minkowski spacetime. Everything's perfectly nice. So if you do have this idea, then indeed, I can see how you would have this you would have this sort of view. I think that it might be the case that there might be some singularities which arise through topological reasons alone, rather than through unusual features of the space-time. Maybe I can try drawing an example in the corner here to give you an idea about something that I have in mind. All right, as I mentioned to you, I'm not as practiced as I used to be at this, so you'll forgive me. So here, I'm drawing a cone that has an open endpoint, and I'm inviting you to imagine that this cone is a two-dimensional relativistic spacetime, and it's flat, and the light cones everywhere are positioned like so. So you can see the light cones here are all pointing upwards in this representation towards this empty point. That's what this little loopy thing is supposed to be representing. So you can see what's happening is that a curve coming from this direction and a curve coming from this direction are both going in a future-directed manner, and they're both geodesics because the space-time is flat. But the space-time can't be continued at this point here because there's no smooth way of connecting opposing light cones that would be going in different directions. So this space-time would be considered singular, and if you allow for the cone to extend out below, it's also inextendable. So this would be an example where a space-time singularity arises for purely topological reasons alone. And it's so even in a situation where the space-time is otherwise flat, every region of it is nice. Every open region of it is nice. So if you think that this sort of thing is possible, it might weaken your resolve that space-time singularities have to rise because of some violent gravitational effects. On the other hand, if you think that this sort of example can be excluded for other reasons, you might be able to hold on to the intuition that you were expressing before.
Okay, let me ask a sort of broader methodological question. So it seems to me that, you're sort of, or at least this kind of literature or debate is assuming that we can look at different spacetimes, have some judgments about whether they're singular, and then try to construct definitions that sort of capture our judgments that are sort of not pre-theoretic, but sort of rigorous theoretic, right? And I mean, I'm sort of skeptical that this is a methodology that will be successful because the notion of singularity isn't the sort of thing that we can have sort of reliable judgments on. You sort of mentioned this earlier. And I imagine the more sort of logical thing to do is to sort of first, build really good theories that do a lot of explanations that we want, and then maybe we can see whether they have in them good definitions of singularities, and if they don't, then so much the worse for our project of trying to come up with good definitions of singularities. So I'm not sure that this is necessarily an objection to anything that you've said, but I feel like it slightly has a different kind of prediction of what we should be working on, because it would be suggesting instead of trying to sort of avoid counterexamples, and construct counterexamples, what we would be doing is looking at the spacetimes that people already take to be interesting for different physical reasons, and then to see within them what kind of notion of singularity there might be.
Yeah, I mean, I'm very sympathetic to this sort of idea, and I think that this is a methodology that many people do pursue. But the problem is that from these limited set of examples that people find, there's different ways of inductively generalizing to a category or to a criterion. Um, and so how do you resolve these disagreements? Part of the reason why I've sometimes framed things in my discussion here in terms of people's intuitions about whether examples are intuitively singular or not is that if you don't work on this topic, this is the most easy and natural way to get into thinking about it. And most of the kind of preliminary discussions that folks have when they're first starting to think more deeply about this topic involve these appeals to intuition. And I think that, and I don't want to be too down on that because that's a very natural way to get into thinking more deeply about a topic. And I think in our Q&A period, right, that's the kind of methodology that in several examples we've been discussing have. But I agree that once you try to be more systematic about it, it's got to go beyond intuitive judgments about particular examples to do something a bit more systematic. Um, but it doesn't seem to me that there is yet a natural definition that everyone's agreed upon. I think what's happened is that because the singularity theorems use geodesic incompleteness, and you consider that, and everyone, by all accounts, considers that to be a sufficient condition, that attention to this particular problem has kind of fallen away. But with a bit of irony, because I think that in a lot of examples where people want to resolve singularities, it's often because they want to resolve cosmological singularities or black hole singularities or naked singularities that can form under certain circumstances. I think that instead of thinking about those examples using idealized models, you might think about them using more complicated examples. But as we all know, because all of us here think about GR quite a bit, it's very difficult to hold in your mind complicated relativistic spacetimes, the ones that we can really think about easily without applying computational methods, for instance, are ones that have a ton of symmetries typically, or that are directly related to ones that have that. And so if we want to have a general methodology for understanding what we're trying to resolve, I think some attention to this sort of problem is needed. And I think that's compatible with what you say, Siddharth, that this is just a kind of a methodology which is an entree to thinking about it in a deeper and more systematic way. Does that sound right to you?
Yeah, Ramesh, you have a point.
Yeah, you mentioned the singularity theorems. So, Penrose gave this theorem. He said, if I have such and such conditions, I will have geodesic incompleteness. And yeah, so that's a problem. With these newer definitions of what is incompleteness, you've got different definitions of incompleteness. What does it do? I mean, does it loosen Penrose's theorem, or is this theorem still okay with all these newer definitions?
His theorem is still okay, and the reason why is that all of these definitions that I've been considering here, they all agree when it comes to geodesics. So if a curve is geodesically incomplete, it'll still be a witness to the spacetime being singular even on these definitions. What these definitions are trying to capture is the possibility of witnesses to the spacetime being singularity that are not geodesics. But if you're just focusing on geodesics, then they all agree with one another.
Great, thank you.
Okay, unfortunately, we are at time, and so apologies to people on the in the Zoom who may have questions. I'm sure Sam would be happy to take your question over email. So please
Yep,
feel free to
definitely.
speak to Sam, and we'll see Sam again next week. He's going to talk about a completely different topic, which has to do with the local Minkowski nature of spacetime. So we'll see Sam in a week. Thank you, Sam.
Thank you, everyone, and thanks for the great discussion.
Okay, bye.